Okay, this is the mini project. This is one of the applications that I was planning to do for you in the class. That is the Cochlear signal processing. Cochlear does amazing signal processing, and what I thought was use this as an application and also do it as a mini project. A person speaking, which is a transmitter, that's your waveform, any waveform, in this case, how are you? And this is your receiver, that's your ear, that's your receiver. And the speech waveform going through the ear canal and causing the eardrum to vibrate, and that vibration is transmitted through the middle ear to the inner ear, which is what we are going to model, which is the cochlear, and the output of the inner ears are impulses. So all these are filters. So we will implement the middle ear and the inner ear as a cascade of filters. So what's the project outline? Let me just look at the project outline. This is a mini project done individually. It's not a group. You can work in group, but we expect you to do as much work individually so that you have the knowledge actually. And then you will be assessed individually, but you can discuss as a group, which gives you better understanding. So we will focus on the understanding and modeling of a spectral analysis. So the cochlea, the inner ear, does spectral analysis, and I will explain that a bit more, carried out by human cochlea. So there are three parts to this project. The first part, which is part A, is basically the explanation of the human auditory system. You can actually follow my lecture, or you can go through a YouTube. Various lectures are there as well. The second part, part B, is the implementation of the cochlea as a cascaded filter, as a transmission line. When you cascade them, it's like a transmission line. And part C, I have included some guidelines for you, so that as you implement them, you can check whether you are on track. So there are three parts to it. So this video is for part A, and you can get additional information. You can look at a lot of animations available on YouTube, and I have given you one example of cochlear animation, and similarly there are a lot of other animations available. I encourage you to watch these animations. That gives you a bit deep understanding of what you are going to do. So the mini project will involve modeling the following. The first one is you will understand the analytical models describing various elements of the peripheral auditory system. An auditory system is outer ear cascaded with the middle ear, cascaded with the inner ear. There are three parts, all of them are cascaded. They are all filters actually. So then the second part is implementation of a digital model of a peripheral auditory system in MATLAB. And then third part is that you will demonstrate it, validate your implementation, and I have given you some guidelines, and then you have to present your work and we will assess you. So how do we assess them? In week 10, as you know, every student will be allocated 15 minutes maximum, and you will approximately 15 minutes where a tutor will assess your work individually. And when the tutor is assessing, we will be looking at how you are able to demonstrate your model and the implementation of the model. You need to explain how you have done it, and then you need to show your code to the tutor, and then tutor will ask questions, trying to see how much you have understood in the implementation. So you have to demonstrate in-depth understanding, and then you need to explain the project very well as well within that time. During that time, the tutor will give you, ask you to do a modification to your code, and you should be able to type in a couple of lines to include that modification and run the code. Or the tutor may ask you to remove a couple of lines and and ask you to explain what does that mean, what are you doing by removing it. So you need to have a really full understanding. You have to write the code, then only you will understand and able to answer these questions. And then at the once the assessment is finished, then the following week you need to submit your report. The report length is about maximum 4,000 words, and that explaining your project. And you need to start the work immediately. Immediately in the sense is that you need to do part A, understand, then start on part B. And week 8 onwards, you should really do regular progress. You can't do everything in 1 week. But week 10, the first couple of days, we will give you enough support if you are running into a problem in the programming. But I would expect you to implement them well in advance. And we've got 2 tutors available, Sally and Kavya. You can email them if you are running into a problem in the project, and they'll be able to help you. But my suggestion is that you can work together first, but then if you really can't implement, then email them rather than just for every question, rather than emailing them for every question. It's okay. Thank you. Now we look at cochlear signal processing and part A. I'm going to explain the introduction to human auditory system, and then, as I said to you, what's the outer ear and what's the middle ear, and a learning activity which you should try it out. There's no assessment on the learning activity, but just by doing that you will be able to implement filters afterwards. Then the inner ear, then the organ of Corti, what is organ of Corti, and all these are filters, these are sensors, they're sensing the signals. Filter output being sensed by hair cells. So I'll go through this now in a minute. So introduction to auditory system, and you can see that the sound wave is coming in here, it's going through the ear canal, and that we call it as an outer ear, and it's a resonator, it's a bandpass filter. I'll show you the frequency response, the magnitude response in a minute. And then you've got 2 bones here who actually, this vibration, this eardrum vibration is translated by those 2 bones, and there's something what we call a stay piece, that's the next one, which actually pass the signal through, there's liquid inside, and it's pushing the liquid, and the stay piece move in and out, and a transmission waveform is set up, fluid waveform is set up. I'll go through the detail in a minute. And that's called the inner ear, which does the Fourier analysis basically. So this is a resonator selecting, and this is matching the impedance. So this is mechanical movement, and then mechanical to hydraulic movement, and there's an impedance matching is done. And so the human auditory system is responsible for converting the pressure vibration caused by a sound wave and interpreting, and then it's converted as a nerve impulse at the end here, at that point, and that's being interpreted by the brain. So human auditory system is designed to assess frequency and amplitude. That's the main part of it, but there are other things also. The peripheral auditory system is divided into outer ear, middle ear, and inner ear, as I explained to you, and it can be viewed. Cochlear, the inner ear, can be viewed as a real-time spectrum analyzer. Basically, it's a filter, many filters there. So the primary role of the cochlea is transform an input signal, which is a complex signal, it's not sine wave alone, it's just a complex, any speech waveform, any waveform, and getting in here, causing the vibration of the eardrum, and then it's translate them into electrical signal. That's here. So a mechanical vibration here is translated into electrical signal that goes to the brain. So a human ear can respond or variation in the frequency range of like 20 to 20 kilohertz. That's the human auditory range. Just to get a little bit of idea here, the level of the sound. When you provide a 20 dB at that point, at 20 dB, and it's called faint to whisper. So humans should be able to hear 20 dB. So it's like hello, very whispery behind the ear. That's about 20 dB. And a normal conversation between two people are between 40 to 60 dB is the normal conversation. And very loud sound is about 90 dB. So things like blenders and concerts, and they are about 90 dB. And then when you reach about 120 dB here, at that point or here, and you reach a level where you will find it's very uncomfortable at that level. And this level is too difficult. Whenever you reach that level, you automatically will close your ear because it reaches a level of pain, and you will stop. So this is just to give you a range. So the ear is able to code anything between 0 dB to 120 dB, and it compresses that into a small range and send it as electrical impulses. So the range here is roughly 0 to 120 dB. That's the maximum range. If you try to anything more than 120 dB, there is a saturation effect will happen here, and also it reaches the level of pain, and then you will normally close your ear. Anyway, so we are interested in the outer ear. First, outer ear is called the resonator. Outer ear is only that part. So these are pressure waveform traveling through this ear canal of length of L, and cause this pressure waveform cause this eardrum to move, eardrum to vibrate. Without going through everything in detail, if you look at the frequency response or maximum response of the ear canal, it goes from this to this range, and it has got roughly a resonant around 3 kilohertz. That length corresponds to, resonant rate is about 3 kilohertz. So it's like a broad bandpass filter. So the outer ear looks like a broad bandpass filter. So this bandpass filter can be implemented using pole zero placement or any other method. And I've given you all the details here, so you can just read through them. Now we move on to the next slide. Next slide is the middle ear, which is the impedance matcher. What does that mean? There are 3 bones available. This eardrum vibration make this malleus to hammer. Malleus is like a mallet, and this incus is another like an anvil. So it hits like this one. That causes this to move, and then that causes move the stay piece. So that's you can see that this is the eardrum vibration. This is the malleus. That's incus, and that's connected to stay piece. And this move in and out. This is the cochlear part, and that's the cochlear. We'll come back to that in a minute. So what's the middle ear? What does that do? So it's translated the mechanical movement. This is the mechanical movement, and matches, impedances match, and a small pressure here, very small pressure will give a large pressure here to push the liquid through this cochlea, which will come back in. So you can see that the middle ear transforms the vibrating motion of the eardrum into stay piece via 2 tiny bones, malleus and incus. Let's move on to the next part. And you can see here, this is again the pressure here, the force there is 1 point, force at this is the oval window, this part. The force there is 1.3 times of what's in the eardrum. And eventually, if you translate them into pressure at the oval window is here, the pressure there is 25 times of the pressure here. So it's just a translating, it's like an amplifier as well. So what does that look like, middle ear? If you actually measure the frequency response on the middle ear, and it's 10 kilohertz range, it's like a broad, a low Q band pass filter, but it doesn't select anything, there's a slight selectivity here. So if you take the outer ear and the middle ear and you cascade them as two filters, you will find outer ear is at 3 kilohertz resonance, middle ear is something like more broad, and if you combine them, you get something like this. This is your frequency response of combination of outer ear and the middle ear. These are just based on measurements. So your first activity that you'll be doing is you'll be implementing this and you'll be implementing this, you're cascading them and trying to get that sort of a graph. That's your activity 1 and 2. So once you have done that, then we move on to the inner ear. So I've laid down everything in part B, but let's move on to the next section. So once you have done all of this, you need to look at reflections. You need to go through these questions, this one and this one and this one, and try to answer. If you don't understand, go back to the notes or watch a video on YouTube. And here's the learning activity. This learning activity is the implementation of these middle ear filters as well as the outer ear filters. And you can use MATLAB to implement this. And I think our implementation next page should show the implementation. So you can implement them using pole zero placement. I've given all the equations for you, and you can use this to implement. And if you do that, you have to place the poles and zeros in the right place. You will get the outer ear there and the middle ear here. And when you combine them, this will be your combination filter. These two are combined. Now, you can make variation to it, but don't look at the pole zero here directly. You start to think, if you want a resonance around 3 kilohertz, what you need to do and how you design it, and play around with the pole zero placement in MATLAB to get your filter designed. So I've given you enough details for you to implement this. Now we move on we have looked at the outer ear, we have looked at the middle ear, and we have implemented, that's the activity 1. Now we move on the inner ear, that's the spectrum analyzer. So inner ear, so this cochlear, you need to uncoil them, because then you can understand better. So inner ear consists of the cochlear responsible for converting the vibration of sounds into electromechanical impulses, which are passed to the brain. So it's a spiral-shaped structure. When you uncoil them, it's like a 3.5 turns, it looks like this. So this is your outer ear, this is your eardrum, this is your middle ear, and when you move this one, this tape is move them here, and you can see this cochlear, when you uncoil them, you can see that there is fluid in there and fluid in there. This fluid is called scala vestibuli, this fluid is called scala tympani, and when you make the movement here, you set up a waveform and the liquid, a traveling wave is set up, and the traveling wave travels, and these two liquid are separated by a membrane called basilar membrane. Basilar membrane, you can think them as a resonator. Think this got 5,000 points on the membrane, and each point is a resonator. Somehow they're coupled, and that's the membrane. So this part of the membrane is sensitive to 20 kilohertz, and this part of the membrane is sensitive to 20 hertz. Now in this case, somewhere here there is one signal which is in the middle part of it is traveling, and you will find the membrane start to slightly move and give maximum deflection at the point. So this is distance and frequency, and this is deflection. So if this wave, so let me now go through further. So if you say this is 1 kilohertz, this will move and set up a waveform, a liquid pressure waveform traveling a liquid, and it will travel, and wherever it's 1 kilohertz, if that's the 1 kilohertz position, the membrane will give you maximum deflection, and the wave does not travel any further. So if you have got hundreds of frequencies, then you will have many places vibration. They each one responds to one frequency. And at this point it's called round window. When you push the liquid that direction, this will push that way. That's how it's balance the pressure. And you can see if when you uncoil this cochlear, it's like this, and that's the top part, that's the bottom part, that's the top part, that's the bottom part, that's your membrane, sensitive resonating membrane. And you can see this end is called basal end, this is called base end, basal end, this is called apical end, and apical end is roughly sensitive to about 70 hertz. Or for 20 hertz there, and here is around 20 kilohertz. Okay, so that's cochlear. Now you're going to model this one. How are you going to model? That's what. So it's a spectrum analyzer. So let's go further. Now, without me reading through everything. So the membrane, the basilar membrane, that this membrane. If you look from the top, you will find the membrane is like when you uncoil them, it looks like a trapezium type, and a smaller width here, and the width increases as it goes this direction, and there's an equation for that. The length of the membrane is 3.5 centimeter. The cochlea is around 3.5 centimeter, and there's an equation, the frequency at which it resonates, each point is sensitive, that point, all are sensitive, and is normally calculated like this. You can have this one as 20 kilohertz if you want to start at 20, or 24 if you want 24, and x is the distance, here x is 0, and here x is 3.5, sorry, that's 3.5, and you substitute, you get all the frequencies. The resonant frequency of each point on the membrane can be calculated. So for an uncoiled cochlea, here you see traveling wave in the basilar membrane, and this moves at a particular frequency, and the wave is traveling, and you can see, and at that point, that point is sensitive for the frequency that's coming in, so that vibrates, and that does not travel any further because all the energy is being absorbed there. So the basilar membrane is a resonant structure that vibrates vertically, in sympathy with the pressure variation in the cochlea. Let's go to the next part of it and look at the basilar membrane again. Now here, I'm giving a frequency of 100 hertz and at the eardrum, and it's traveling. 100 hertz belongs to apical end. So this part of the membrane is not affected, and as it goes, this part is sensitive to 100 hertz, and that will oscillate. Then I give 1 kilohertz, it's somewhere in the middle, so it travels, the wave travels here, and wherever it's 1 kilohertz, it oscillates, and it doesn't travel any further because when it's resonating, all the energy is taken out from there and doesn't travel any further. And when you give 10 kilohertz, it's closer here. This is 20 kilohertz, so it resonates there. So the low frequencies at this end and high frequencies at this end. This is different to FFT. When you do the FFT, your low frequency will be on the left hand side, high frequency on the right hand side. But for basilar membrane, the high frequency is on the left hand side and the low frequency on the right hand side. Right? And here, in this case, I've got 3 frequencies, and you can see oscillation and there, and there, there. So we can say this basilar membrane can be modeled as a bandpass filters like this. So that's what we are going to do. You can read through all of these, and I'm just giving you enough explanation. Let's look at basilar membrane again, and this is a simulation done by us some time ago, and showing us a cochlea as a rectangular kind of a box, and there are 2 frequencies at that point. It resonates at 2 places. And also, if you look at the frequency equation I showed you earlier, at that point is 16 kilohertz. You can make this as 20,000 if you want it, and it decays. The frequency decays, and then comes very low frequency at 3.5 hertz. So somewhere there, that will be about 10 hertz. Anyway, so basilar membrane now can be represented by bandpass filters. So one option is that researchers have measured impulse response on various places on the cochlea, and then they've modeled the impulse responses, and they've given a general equation, and by changing the frequency here, and we can actually find impulse responses at different position of the membrane. Using this equation, you can have 128 filters representing the basilar membrane, or 2000 filters representing the basilar membrane. So your learning activity 2, what is the learning activity 2 is you're going to model this equation, and by changing the resonance frequency, and you can look at the impulse responses, and then you take the Fourier transform of the impulse response, you get the magnitude frequency response, and you can find the maximum response of these impulse responses. So basically, if this is at 1000 hertz, and when you do that, impulse response will look like this, and if you take the Fourier transform of that, that's what the maximum response is. And you can go back to that equation, this equation, and now change this frequency, and you get a different impulse response, and then different maximum response. So that's the second exercise that you have to do. That's your second learning activity. Make sure that you do learning activity 1 and 2. Once you have done these two only, move on to the next one. Once you have done this one, you have a reasonably good understanding of what's a filter design, how you want to design it, how a basilar membrane is represented by bandpass filters. Once you have done that, you can move on to the next one. If you're not sure here in the implementation, then you might email the tutors, right? So I will encourage you to, this part, up to this part, it's not difficult for you to do it. You'll be able to fly through this pretty fast. And here's that learning activity, whether you are on track. You will see I've got 3 filters here, 800 hertz, that's the impulse response look like. For 2000 it looks like this, for 4000 it looks like this, and for 6000 hertz it looks like this. And if I take the Fourier transform of that, that's the first one, the second one, the third one, the fourth one. You can see the bandwidth here is smaller, the bandwidth is bigger as you go along. For high frequency, the bandwidth is bigger. For low frequency, the bandwidth is smaller because you need to resolve the pitch. In order to exactly determine the pitch, the bandwidth has to be smaller. And you can implement, this is only 4 filters, you could make this, if you want a spectrum analyzer, you can have 128 filters. That means 128 impulse response to 128 bandpass filters. You will find these filters are okay to implement, but in real cochlea, when you measure the frequency response, the frequency, for example, if I take that frequency response in a real cochlea, it will be like that, the frequency response. That's frequency, that's amplitude. It's very sharp roll off, and you will not get that sharp roll off like that using the equation that we gave. So this is what observed on cochlear, on the fibers. This is what you will observe in measurements. So therefore, we have to implement that and not that one. That's kind of introduction. Next part you want to know is what we call as organ Corti. So as I said to you, that when the signal travels along the membrane, and let me just go back 2 steps back, just to get a feel for it. So if you go back here, when the signal is, there's three sine waves here, and they're traveling, and it's causing vibration there at the this is the membrane, and here and here. And this vibration needs to be picked up by something. So along the membrane, like along here, there are hair cells sitting on top of it as well. The structure, that's what's called organ of Corti. And these hair cells actually picks up the movement of the basilar membrane and then send them as electrical signal to the brain. So we need to, so the hair cells are held by organ of Corti. It's a structure which holds the hair cells. So that's the next part of it. Because you've implemented all the filters come, the output is coming, and now we need to convert the output into the signal format, into the like electrical signal format, right? When you do bandpass filter, everything is electrical signal. But here in brain, it has to be electrical signal from mechanical movement to electrical. So if I take a cross section, so the organ of Corti is sitting along the membrane. I take a cross section of it. If I take a cross section, this is what it looks like. That's your membrane. And you can see there are 1, 2, 3. There are 3 set of hair cells. Hair cells mean these are the hairs, these are the cells. These 3, the brain sends signal back to these hair cells. And this one is called inner hair cells. Actually bends, this hair actually bends. When the basilar membrane move upwards, the hair actually bend. And then basilar membrane come back to the normal position, hair comes vertically. And this is the one sending signal to the brain actually. So if you look at block schematically, you've got the outer ear, middle ear, basilar membrane. The hair here is picking up the signal, inner hair cell, and sending through a nerve to the auditory system. And the brain then sends signal back, another set of fibers, and make these two change the properties. That's the called outer hair cell. So you may ask me, where does this come into play? So just a simple explanation is that when you are in a conversation, when you are talking, suddenly there's something, a pin drop somewhere, and you are able to hear that. Even though you have a conversation with somebody, the idea is as soon as the brain sees there's something coming from a filter, which is a low level signal, it increases the, if it is receiving a low level signal, it changes the property of the structure, whole structure. And the resonant part, earlier this was your bandpass filter. The bandpass filter now will look like that. That's how it's able to pick up that smaller signal. That's called active cochlear. You are not implementing that. You're only doing passive. So it needs some sort of a feedback to tell the system, change your property. Okay? So that's what the system is here. So signals are going in one direction, the brain, and So this is signals inner hair cells, and that's outer hair cells. Anyway, you can read a bit more about it. We will be modeling this inner hair cell. How will we model them? And that's the next part of it. So I've shown you these hair cells, and for these are inner hair cells at different frequencies, 16, 4, and 1 kilohertz. Think of it this way. So the inner hair cell bends in one direction. So when the membrane goes up, resonate, the inner hair cell bends in one direction. When the membrane comes down, inner hair cell comes vertically. So things are moving one direction and then vertically. It does not go this direction. You see very small inhibition, it's called inhibition. So that's the resting position, that's the excitation position, right? So what do you think in electrical term? Something in one direction and then not on this direction. So it's like a half-wave rectifier. If you have a half-wave rectifier, current flows in one direction only. So we can implement the inner hair cell as a half-wave rectifier. But remember, when this bends, the hairs bends that direction, there's a time involved for it to come back vertically. There's a time constant involved. It's like a half-wave rectifier signal is charging a capacitor, and then the capacitor is discharging slowly. That's the model that you will implement. So the model that you will implement would be is in a hair cell, it's a half-wave rectifier because of one direction, and a resistor and a capacitor, you select the value such that it charges up and then discharges. It's like think of a floater in the sea. So first waveform coming in, the floater goes up, and then until the next wave comes, this will come slowly down, 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 and then next wave comes, goes up. So it's the same principle. It bends in one direction, then it's come back because the membrane is deflected and it's come down. So you can model this as a hair cells. Now one more thing you have to do is, basilar membrane, we are going to model the basilar membrane on bandpass filter, bandpass filter, bandpass filter. This is the input, this is the output of the filters. Remember, they are individual filters. Now we need to couple them. We have to couple them. So the coupling is done. This is frequency. This is, there's no axis. This is frequency. So the coupling is done by subtracting the output of this with that one, which is called the spatial differentiation, we call it. And you will implement that. That's easy enough. Spatially differentiation means not time differentiation. Spatially differentiation means one position to next position, you subtract two outputs together. And that's how you provide the coupling between each section of the membrane. That's we call it fluid cilia coupling, which is a differentiation is a high pass filter. So this is the last part of this actually. So I've gone through outer ear, inner ear, middle ear, inner ear, I've given you some idea, right? And you may not get everything from my lecture. You may want to look up on the web. You may want to read a bit more. And once you have understood, then ask the question, what is a tectorial membrane? What does that do? Which is an organ of Corti. How many sensory hair cells are available? What is the subspectorial space? How many rows of inner hair cells are there? All these ones you need to just ask as a question and reflect and see whether you understood. If not, just go back and read a bit more. There's no exams in this area, but by understanding this, when you do the next part B, modeling, become easier for you. Okay, that's all for the part A lecture. Just a little bit of introduction to a human auditory system, the anatomy and how it works. So, in summary, you are going to think as a pressure wave is converted into a fluid traveling wave. That's converted into a mechanical movement of the basilar membrane, and the mechanical movement of the basilar membrane is translated into electrical signal by the hair cells. So all these are filtering technique. There's nothing different. As far as signal processing concerned, signal comes in and we are going to filter. So that's in part B. So let me go through part B now, and you will have an understanding then how we are going to implement. Thank you.